Our bodies are capable of incredible feats of strength, agility, and endurance. At the heart of these abilities lies a complex network of muscles. Muscles are the body's engine, responsible for every movement we make, from the subtlest blink to the most powerful athletic feat. They are made up of specialized cells called muscle fibers, which have the unique ability to contract and relax. This contraction and relaxation are controlled by signals from the brain, which travel down the spinal cord and through nerves to reach individual muscle fibers. This intricate communication system allows for precise and coordinated movements. When we decide to move, our brain sends an electrical impulse to the motor neurons in our muscles. These motor neurons release a chemical messenger called acetylcholine, which binds to receptors on the muscle fibers. This binding triggers a cascade of events that ultimately leads to muscle contraction. The force of the contraction depends on the number of motor units recruited by the brain. One of the most fascinating aspects of muscles is their ability to adapt to increased demands. When we consistently challenge our muscles with resistance training, they respond by becoming bigger and stronger. This adaptation is essential for our survival, allowing us to meet the physical demands of our environment. Imagine trying to open a heavy door. Initially, you might struggle to generate enough force. However, as you continue to push and pull, your brain recruits more motor units and other muscles to assist in the task. This increased recruitment leads to greater muscle activation and force production. Over time, with consistent training, the muscles involved in opening the door will become larger and stronger, making the task easier. This adaptation is not limited to strength gains. Muscles also adapt to endurance training by increasing their capacity to use oxygen and produce energy. This allows us to perform activities like running or swimming for longer periods without fatigue. The process of muscle growth, known as muscle hypertrophy, is a fascinating interplay of cellular and molecular events. When we subject our muscles to resistance training, we are essentially causing microscopic damage to the muscle fibers. This damage is a natural part of the muscle growth process. The body views this damage as an injury and initiates a repair process to rebuild the damaged tissue. This is where the magic happens. Injured muscle cells release signaling molecules called cytokines. Cytokines are like messengers that alert the body to the damage, triggering an inflammatory response. Inflammation is a crucial part of the healing process, as it brings white blood cells and other immune cells to the site of injury to clear away debris and begin the repair process. This inflammatory response is what causes the soreness and stiffness we often feel in our muscles after a workout. It is a sign that our body is hard at work repairing and rebuilding our muscles. Understanding the science behind muscle growth allows us to optimize our training and nutrition for maximum results. To maximize muscle growth, we need to create an environment where muscle protein synthesis outweighs muscle protein breakdown. This requires a multifaceted approach that encompasses training, nutrition, and recovery. One of the most important factors in muscle growth is mechanical tension. Muscles respond to tension by growing larger and stronger. This tension can be created through various forms of resistance training, such as weightlifting, bodyweight exercises, and resistance bands. Another crucial factor is protein intake. Protein provides the building blocks, amino acids, that are essential for muscle repair and growth. Consuming adequate protein, especially after workouts, ensures that our muscles have the necessary resources to recover and rebuild. Hormones also play a vital role in muscle growth. Testosterone, growth hormone, and insulin-like growth factor, or IGF-1, are anabolic hormones that promote muscle protein synthesis and inhibit muscle protein breakdown.